Hello everyone, Alfred Cromwell here, and as I promised you in my last video, this video is going to be about Rolle's theorem and also the mean value theorem. I figured I'd mention it because the mean value theorem is very much related. So in the we're gonna what I'm gonna do first in this video is kind of go over the what when it applies, but I am assuming a certain prerequisite knowledge. Now, if you have not taken calculus, then you should not be watching this video because you're not going to understand or if you don't understand functions, for example, you're not going to really have a good background to understand the material in this video. And we're going to be talking about because we're going to be taking a moment to appreciate the beauty of continuous functions. And if you don't know what a continuous function is, as I said, you should not be in this video. You need to go back to algebra, algebra 1, algebra 2, where you can discuss what that is. So if we take a moment to appreciate the beauty of continuous functions, it's kind of like they're sort of like, I'm always reminded, they are like good friends. They don't suddenly ghost you, and they're always there in a way when you need them, smoothly sort of bridging the gap between A and B. Now, imagine that you have a function defined on a closed interval, AB. And I'm going to show you a diagram, but just bear with me for a moment, but just think about it in your mind. A function defined on a closed interval. And somewhere along this journey, the function sort of peaks or valleys, if you prefer, at a point, at some point where you can say point C is an element of that interval. And it's going to show off its maximum or minimum value, sort of like if we're talking about the maximum, it's sort of like the tallest student in a class photograph. It's going to be interesting, right? The student that is the tallest that usually stands out the most and is very interesting, right? So what's interesting about this tallest student or person? Their graph, you're going to see on the board, their graph sort of flattens out at the peak. And there's no rising or falling. They're just kind of, as the young people would say these days, right? They're just kind of chilling with a slope of 0. And it's sort of the mathematical equivalent of taking a breather after a climb. And there, voila, you get the tangent line at C of f of C. So I want to show you on the board kind of where I'm coming from with this so that you see there's going to be some graphs today. And then we're going to talk about Rolle's theorem and all those definitions. All right, so hopefully you can see the problem here because we've been talking about the closed interval, and you should think at this point about what do you know about the derivative at that point. And I'm going to show you sort of a sample sketch, and it should give you some idea. Now, I was talking about flattening out, and I was referring to something that looks like this. All right, notice what's happening here. You see that the graph tends to flatten out at that maximum. And so you have a tangent line at the points, as I was saying, C of f of C. The point there is horizontal. And so that leads us to a conjecture. And the problem that we should think about is this problem. I want you to read the problem. Let f be a continuous function on a closed interval, and let C be an element of A and B. Let's that be a point at which f attains its maximum on AB, on that closed interval. And show that if f is differentiable at C, then f prime of C is equal to 0. So when we conjecture this, I want you to think about it. I want you to pause the video, kind of think about it, do it on paper, and we're going to prove this. But there are some, I warn you, there are some plot twists. Because the max might be at an endpoint. So if you're standing at the edge of a cliff, you can't really expect a horizontal tangent line unless you enjoy falling off. And in the society we are living in, I wouldn't be surprised if there are people who actually would enjoy that. We see it a lot there have been reports I read recently, some reports coming in from, kind of off topic, but some reports were coming in from Europe. They were saying that some young people, some English young people, I think specifically English, not just British, or not British as a whole, but they were actually there's a phenomenon called balconing. Which means that when they visit places like Spain, they jump off balconies. And so I wouldn't be surprised. That's why I mentioned, if these days. But anyway, so the other thing to consider here is that the function might not be differentiable at the peak. If you think of sharp crests, like a mountaintop that cuts the sky. So just take a moment to consider the derivative of this, and then we'll talk about it. So by now you should have paused the video, and I want to show you, before we go over the solution, I'm going to show you some graphs that show those subtle yet important conditions, right, that I was talking about. So if you want to see it visually, this is what I was talking about here, right? So think about this for a moment. So now let's talk about the solution. If we're going to let C be an element of AB, if we're going to let that C be the point where F gets its maximum, we're going to have to write the definition of the derivative, right? F prime of C. Now the derivative, I'm going to write it out because I don't like typing. So do F prime of C. And if we do a derivative here, we're going to say the limit as h approaches 0. And the definition, of course, is f parentheses c plus h. You should know this by now, if you've taken calculus, or if you have some familiarity. So minus f of c. And all of that is going to be over h. I don't like the way my h looks. It looks sloppy. That's better. All right, now we have to, of course, assume that h is small enough, right, so that c plus h, right, is an element of that interval, right? So what do we know? What do you know about the numerator in this? This is a fraction. Well, since f of c is the maximum value that f attains, you know that f of c plus h has to be less than or equal to f of c. Let me write that down in case you're not familiar, but hopefully you know what I'm talking about here, right? So that has to be less than or equal to f of c. So in other words, the numerator has got to be either 0 or negative. But the denominator has to be positive, for h has to be greater than 0, of course. And if h is less than 0, it'll be negative. So if you only think about positive values of h, you're going to see that the derivative, f prime of c, is going to be less than or equal to 0. And if you consider only negative, you're going to see that it's going to be greater than or equal to 0. So the only possibility is that f prime of c is 0. And of course, essentially the same argument works for the minimum value of f on the closed interval AB. We now have so now we can create a theorem, right? And you can look at the theorem. It's I call it the peak or pit plateau theorem, which basically says if f is continuous on AB and differentiable, then at a maximum it's going to be f prime of c equals 0, and at a minimum f prime of c equals 0. All right, so let me actually, it's going to take, I wanted to make a short video, but let me see if I can be quick and give you the theorem. And the theorem, if I write it out, f must be a continuous function on a closed interval. And the first thing is, so if the function attains its maximum at C is an element of A and B, and very important, f has to be differentiable at C. Then what this means is the f prime of C equals 0. Likewise, I notice I didn't put an f in here, if f attains. Now for the minimum, same thing, but we'll just call it, instead of at C, we'll just say at D. Then the derivative at that point is going to be equal to 0. Then f prime of D is equal to 0, all right? So remember, once again, you have to remember the important exceptions to the theorem, because f might not be differentiable at its minimum or maximum, and the minimum or maximum might occur at one of the endpoints of the interval. So if we change the conditions slightly to remove those exceptions, we actually get a very useful theorem. This is where Rolle's theorem enters the room. What if f of A, in other words, what if f of A equals f of B? How about that? Well, that's like sort of saying you start and end a hike at sort of sea level. Somewhere along the way, you must have had a horizontal moment, and that is Rolle's theorem. It's kind of like the sibling who's always flatlining, figuratively. So the theorem says if f is continuous on AB, and differentiable on AB, then something very interesting happens, right? And f, of course, f of A has to equal f of B. So what happens with that? There exists C as an element of AB, such that f prime of C equals 0. And so the easiest way to remember this theorem, let me show you a diagram so that you can keep this in mind. And that's going to be the easiest way that you can remember. If you keep the following diagram in mind, okay? Because if you see a continuous function here, it starts and ends at the same value for f of a and f of b. So it equals each other. So it must flatten out at some point, c, when f of prime of c equals 0. It's a very nice theorem, actually. But it's very specific. It's pretty specific here. It only works if f of a equals f of b. But we'd like a more general version that works on any differentiable function on an interval. So if you think about Rolle's theorem, no matter how wild the ride, if the function starts and ends at the same height, it has to pause mid roller coaster for a zero slope breather. But then you get Rolle's big brother here, the mean value theorem, otherwise known as MVT for abbreviation. So their sibling here is the kind of like the life of the party, the calculus party. If you think about it, if you consider an arbitrary function that's continuous on a closed interval and differentiable, and let me see if I did a little diagram earlier and I can't find because all these diagrams that I'm trying to do my best to show you, hopefully it's going to come up. All right, hopefully you can see it. So notice what happens here, right? If you sort of tilt your head and pretend that the x-axis runs through a f of a and b f of b, as you can see, you can get the idea that we should be able to find a point, c being an element of ab, such that the tangent line, notice that the tangent line is parallel to the new x-axis. And what does that mean? What does that really mean? It means that the tangent line through CF of C is parallel to the line through A f of A and B f of B. And of course, by parallel, it would mean that the two lines have the same slope. So if we put it all together, we can have the mean value theorem, right? The mean value theorem is, you can think of it as the slope of line through A f of A and B f of B. So the theorem says if f is a continuous function on the closed interval, so let me write it out now that we're already doing it. So always, again, continuous function. And it's always on the closed interval. And A has to be less than B, of course. And we have to say that f is differentiable on AB. So the theorem says that if given these conditions, there exists some real number that looks as follows. So we can write it out as f prime of C is equal to f of B minus f of A all of this over B minus A. So arguably, the mean value theorem is the most important theoretical result about the derivative. You should think about the mean value theorem until its statement becomes intuitively obvious to you. Now, the proof is a little bit tricky. I'm not going to do it in this video because this video I was going to show you some of the problems I wrote about Rolle's theorem. But so the proof is a little bit tricky, but I will defer it. But you will see a lot more of the significance of the mean value theorem as you study more and more calculus. So basically, in summary, Rolle's theorem is the special case where the start and end values are equal, and it guarantees a zero slope at some point. And the mean value theorem generalizes this and ensuring there's always going to be a point where the instantaneous slope matches the average slope over a b. So hopefully that clears that. I tried to give you a rigorous definition. Hopefully that clears that up. And now we're going to see some basic problems. This is from I told you, if you watch my previous video, which I'll link down below with the announcements, I told you that I was preparing a book of 534 solved math exercises. It's not a textbook. It's just kind of like, if you remember back in the day, I don't know if they still have them around, Shalm's, I think it was Shalm's outlines. Those, it's sort of like that where they just solve problems, and you just, so it doesn't include any theoretical. I mean, it'll have some tips and things like that, but it's mostly just solved problems, starting with we have vectors, trigonometry, and up to the calculus level. So it would be a good book for those of you who are in pre-calculus or even calculus. In fact, I've also included at the end, I'll be including some probability questions as well, or statistics, because not because I enjoy it, but because I know a lot of students are nowadays with the new math, they are taking some of that. And plus it's not a bad thing to know. All right. So hopefully that clears it up. And here come the problems. All right. So to verify the first these are problems from my exercise book that I mentioned earlier. So the first one is, it says verify Rolle's theorem for the function f of x equals x cubed. Doesn't look okay. There we go. For the function f of x equals x cubed minus 4x plus 1 on the interval 0, 2. Well, first of all, we're going to when you solve a problem like this, let's actually check for the conditions of Rolle's theorem. Remember, Rolle's theorem states that if f of x, if the function is continuous on the closed interval ab, f of x is differentiable on the open interval ab, which means that f of a equals f of b. You already have the theorem that we talked about earlier. That means that there exists at least one c as an element of ab, such as a derivative f prime of c is equal to 0. And the function that you see here, well, I want you to try it first and see what you come up with, and then we'll talk about it. All right, did you pause the video? If you've paused the video and you have an answer, let's do this. You have the function is x cubed minus 4x plus 1. Well, it's a polynomial. It's a polynomial. So that means that it is continuous and differentiable everywhere. So that means that f of x satisfies the first two conditions for Rolle's theorem. And now we have to compute the endpoints here, right? So we're going to compute f of 0. And if we do f of 0, we have 0 cubed minus 4 times 0 plus 1, which equals 1. And if we evaluate at 2.2, we have f of 2, which equals to 2 to the third minus 4 times 2 plus 1. And that's actually going to give you 1 as well. So The third condition is satisfied, right? F of 0 equals f of 2. So we have our conditions here. Now, we need, once we do this, all the conditions of Rolle's theorem are met. And now we compute the derivative. And again, this video, if you have not done calculus before, it's not going to make sense. If we compute the derivative, we have the original function is x to the third. So we're going to apply, it's going to be 3x squared minus 4. This is the derivative. And in that case, you're going to set f prime of x to 0. We're going to find the critical points. So if we set this equal to 0, we're going to do some algebraic manipulation here, right? So if we divide by 3, we're going to have x squared equals 4/3. Right? And then we take the square root, of course, because if you square something, remember you from algebra, you have to do the inverse operation. So if we take the square root, we have 2 over, plus or minus, 2 over radical 3. All right. Now, only x equals 2 over radical 3. Only that point lies in the interval 0, comma 2. So if we actually simplify this, we have to rationalize it's called rationalizing the denominator here because you have a root symbol. So you're actually going to get 2 radical 3 over 3. So that means that the value here of c, f prime of c, equals 0 at this point, 2 radical 3 over 3. Right? So the formal way to write that would be the proper way. If you indicate it as c equals 2 radical 3 over 3 and that is an element of 0, comma 2. And we found, in that case, f prime of c equals 0. So what is the conclusion here? We verified Rolle's theorem on the interval 0, comma 2, and with the point c being 2 radical 3 over 3. All right? The next question. So I've shared two, that's the first one. Here's another one. Can you apply Rolle's theorem for the function f of x is equal to x squared minus 4 over x on the interval negative 2, comma 2, and why is that? Well, again, we already talked about the conditions that you must hold for Rolle's theorem. So f of negative 2 has to be the same as f of 2. So if we check for the continuity here, we have a function here that is going to be, unfortunately, undefined at x equals 0. You are not allowed to divide by 0. Therefore, we say that f of x is not continuous on the interval negative 2, comma 2. Because what's going to happen is there's a discontinuity at x equals 0. Now, what about the differentiability? Right? Well, the issue is if it's not defined at x equals 0, then it cannot be differentiable on negative 2, 2. So even though you can evaluate the expression for negative 2 and 2, because there's a lack of continuity, even though you get 0 in both cases, because there's a lack of continuity, and the lack of continuity and differentiability invalidates an application of Rolle's theorem. So it doesn't apply in this case because the function is not continuous or differentiable on the interval due to the discontinuity at x equals 0. So I hope that this video was helpful to you. If it was, please always subscribe and help this channel grow. Thank you to all my subscribers, and you'll have more videos coming up later on in this week. Thank you.